Alright, so in the previous class we had learnt a few things. I would like to recapitulate one after the other. So the one thing that we had done is that given any vector space V and a vector space W, in V you have dimension n, you have an ordered basis A, here the dimension is m, ordered basis is B, so these are ordered basis, and the dimensions are m and n, whatever those dimensions are, fine. If T is a linear transformation from here to there, so T is from V to W, a linear transformation, alright. So if T is a linear transformation, we have T of V is equal to some element of W, but if I want to write it in terms of B, so TV is an element of W, so I can expand it in terms of W, elements of basis of W. So this is going to be, since it is dimension m, so this vector is going to look like some beta 1 to beta m, and we wrote it as T of AB here, and then V is an element of, so this is an element of capital V. So there is a basis A here, and this has n components, so you have got alpha 1, alpha 2, alpha n. So I am going from n vectors to m vectors, so this vector, this matrix has to be of the size, just look at it, matrix multiplication, m cross n, fine. That was the idea that we had, and here if I look at T of AB, T of AB was achieved as, so look at this has a basis, so we wrote it as a V1, V2, Vn ordered basis. Then we have to compute T of V1, T of V2, T of Vn, we have to compute them, and then we have to write them with respect to the basis B because they are elements of W. Is that okay? So once I write them as an element of this, so each of them is a m cross 1 vector. So total we have a m cross n vector. Alright, so we have a matrix of size m cross n, fine, m cross n matrix. So this was the idea of TAB. We had used this TAB to write the matrix of rotation. We wrote it counterclockwise rotation, counterclockwise in R2 by an angle theta, and it gave us the matrix as, the matrix M corresponding matrix was cos theta minus sin theta, cos theta. Alright. So I would like you to verify here that determinant of M is 1. That's very important. So determinant of M is 1 means that directions are taken care of. Well, this is what we are told about determinant, that when it is positive means that directions are okay, it's a meaningful object, fine. I would also like you to see that this is indeed this, because if I look at any point here, suppose there is this vector which is cos alpha sin alpha, then let us multiply and see what happens to m of cos alpha and sin alpha. Then this by definition is, just multiply it, first component is cos theta cos alpha minus sin theta sin alpha, and the denominator is sin theta cos alpha plus cos theta sin alpha, which is nothing but cos of theta plus alpha and sin of theta plus alpha. So it is indeed a rotation, all right, indeed a rotation by a angle theta, all right. Earlier the vector was of cos alpha sin alpha, means there was already rotation of alpha. Now I am rotating by theta and I am getting another vector, fine, and this is what it says. Now, so the idea of studying such things is also that one has to take care of. For example, if I want to look at R3, all right, and I have a robo, I want to move that robot from one point to another point, from this point to this point, or from this point to this point, or from any point to any point, then I should be able to understand what are called rigid motions. So we need to understand what are called rigid motions. Not in the syllabus, but you need to understand that rigid motion means you are trying to move one object to the other object. So if you look at R3, the movements that you would like to have is what are called translations, and then it turns out to be reflection and rotations. So using these three, you can show that all the rigid motions can be done, that whatever you want your object, whether it is a pulley or whether it is your what do I say, any object that you want to move, motor or robot or anything for that matter, or truck, these three things will help you get the things. Fine. So for example, I have an object which is lying here, say, so this is my origin and this is my object at P. I want to move like this, all right. So this length is not the same, this length is, so I want to move it to Q. So the length is not the same, so OP, length of OP is not equal to length of OQ. So what I can do is that I can move this first, translate further, so that the length becomes OK, so that length of OP prime is same, and then I can rotate it and then rotate, or I can first rotate and then increase the length, all right. So that increasing the movement from one P to P prime is called a translation. So such translations are not linear transformations. Why they are not linear transformations? Basically because T of 0 is not 0, all right. You are not able to fix, because since you are moving it away or going to move it near, whatever it is, this 0 will get disturbed. So translation is not there. As a rigid, it is a rigid motion, but it is not a linear transformation. But reflection and rotations are, and therefore if you want to move something in R3, you don't want to move. So if I want to move from here to here, I can just move my hand like this. I don't want to start from here, come back to the original place, origin, and then go like this. I don't want to do that. Fine. If I want to move from here to here or here to here, whatever I want to do, I should be able to do it in one go. If I am able to do it in one go like this, all right, so it is just a rotation that I am looking at. So when I want to rotate it, it means that there is a plane in which these 2 points are. So origin is at one point, this is at another point, third point is this. So using these 3 points, I can get a plane in R3. Once I have a plane, I need to rotate it in that plane itself. Is that okay? So since I want to rotate in that plane itself, it means that in R3, if I want to look at, there will be plane which I will get here. For example, this will be the plane. As such, it is a XY plane. But in R3, I will have a plane, 0 is there, then the point where P is there, point Q is there. So these 3 points will give me a plane. So I'll get a plane like this. Get a plane which will be something like this. And there is an object here, and I want to rotate by angle some theta to get to Q. Is that okay? That is the idea that I have. So you can see that at some stage I am in a plane R2, and therefore the idea of cos theta minus sin theta cos theta will come into play. So you can show that any motion in R3, any rotation in R3 has the form 0 here, 0 here, 1 here, all right. So what you are saying is that there is a plane. So 1 here basically means that if you look at the normal of this plane, whatever the plane I have drawn here, whatever, so you are moving from here to here. So look at the normal, there is no change in the normal as such. Whatever is happening on the plane, the normal does not get disturbed, all right. The normal vector remains as it is, fine. Similarly, we can also have what are called reflection. So let me go to the reflection now. So, reflection. So, I have something here. So, I have the line here y is equal to mx, it is passing through the origin, fine. So, if I want to get a matrix of this, so I will again do a standard basis in R2 itself. So, I am looking at x and y, and I want the matrix of reflection in a standard basis E1, E2, fine. So, what I am supposed to do? If I am writing T as the reflection, then I need to compute what is T of E1, I need to compute T of E2, and again write it in this basis itself. This was my basis B. So, this will be the matrix that I will have, fine. So, I would like you to see that if I have the point here 1 comma 0, I draw a perpendicular. Suppose this is the point which is the reflection. So, this is alpha comma beta. So, what I will get is this point, the coordinates of this point will be alpha plus 1 upon 2, beta upon 2. Be careful, I may do mistakes. So, just look at it. So, I will get this point. Now, this lies on this line. So, beta upon 2 will be equal to m times alpha plus 1 upon 2. This will imply that beta is equal to m times alpha plus 1. Also, since this is a reflection, so this line is, this is perpendicular. The slope of this will be perpendicular to the slope of this. Their product will be minus 1. Slope of the new one is slope. So, this part was lies on y equal to mx. Now, slope product into slope is equal to minus 1. So, slope of this is beta minus 0 upon alpha minus 1. This times the slope of this is m, should be minus 1, implies beta is equal to 1 minus alpha upon m. So, solve these two. So, these two together will imply that 1 minus alpha upon m is equal to m times alpha plus 1, implies 1 minus alpha is m square alpha plus m square, implies alpha is equal to 1 minus m square by 1 plus m square, and this will imply that beta is equal to, so m and m will be there. So, m into 1 plus, so I hope it is 2m upon 1 plus m square. Please verify it, alright. So, what we will get is this matrix will look like 1 minus m square by 1 plus m square, fine. This is the alpha part, and the beta part will be 2m upon 1 plus m square. So, you have got corresponding T of E1. For T of E2, you again look at this point E2. So, 0 comma 1, look at this perpendicular here, you get a point here. The coordinates of this point will turn out to be, I will just verify it so that everything is nice. So, I do not know, I do not want to waste my time, I just want to look at things here, 2m upon 1 plus m square I hope, and here it will be m square minus 1 upon 1 plus m square. So, what I know is that determinant of this matrix T, determinant of this matrix, so I am writing T here. So, determinant of T should be minus 1, just check whether it is okay or not. So, let me verify it. So, this is 1 minus m square whole square upon 1 plus m square with a minus sign, minus 4m square. So, this should be a minus, I think, just a minute. So, cos theta should be minus here. So, because it is, so this is equal to 1 plus m square whole square, 1 plus m 1 plus m to the power 4 minus 2m square. All right, I want plus 4, so it should be a minus here. There should be a minus here. All right. So, I get here this plus 4m square divided by 1 plus m square whole square. So, it will be plus 4m square. So, this will give me minus of 1 plus m to the power 4 plus 2m square by 1 plus m square whole square, which is minus 1. Fine. So, this is the correct one. There should be a minus here. Is that okay? So, this is the matrix of reflection. I would like you to check that T of E2 is indeed this. All right, just the way I have calculated, you look at this part. Suppose this point is h comma k, get the point here and then use the slope as well as lies to get the values yourself. Fine. Now, what is more important is, once you have understood this, I would like you to understand that I can make, so let me go here. What I am trying to say is that I can also think of something here. This is the line that I am looking at, y is equal to mx. There is a point here which is 1, so y is equal to mx. So, if x is 1, y is m, fine. So, this is one plane or one line passing through origin, which is a subspace. There is another one which is perpendicular to it. Since it is perpendicular, there will be a point here which is m comma minus 1, fine. So, here it should not be minus 1 because I am looking at the height is always 1. So, it will be this side, so minus m comma 1 here, fine. So, what we know is that if I look at this line, the deflection fixes this point, does not do anything to this point. So, the deflection does not do anything, or it fixes the point 1 comma m, fine. And what does it do to this point minus m comma 1? It translates it to the point m comma minus 1, this, and moves the point minus m comma 1 to the point m comma minus 1. All right. This is what the reflection does. It fixes every point here and here, fine. It just does. So, if I want to look at any point here P, say h comma k, what it will do is I can just write P in terms of a projection here, a projection here, fine. This part will get, so if I want to look at the translation here, this will be just look at this part and whatever is this component, it will get added, all right. So, accordingly you can get a point here because any hk can be written as linear combination of this vector and this vector. Is that okay? They are perpendicular vectors, so they are linearly independent and therefore you can get it. So, what we are saying is that if T is a deflection, then T of the point 1 comma m is 1 comma m itself, and T of minus m comma 1 is same as m comma minus 1, fine. So, therefore, what we are saying is that look at T, if I look at this matrix 1m and minus m comma 1, fine, what it does? This is T of 1m, T of minus m comma 1. So, this part remains as it is 1m, this part becomes m comma minus 1, fine. So, this will imply that T is equal to 1m m minus 1 into the inverse of this 1m minus m1 inverse. So, what is the inverse of this? So, look at this, the determinant of this matrix is 1 plus m square. So, 1 upon 1 plus m square comes into play, fine. Then it is 1 m minus 1 times inverse of this. What is the inverse of this? Just look at it. So, the idea is that it should be identity, fine, if you multiply it with this. So, what should it be here? Should it be m or minus m? Where it should be what? So, is there a way to find it out? So, look at the things, this is what you should get. And then you can look at it is 1 plus 1 upon m square. You can use the adjoint method to get the inverse, or just verify that this into this should be identity. So, it is 1 plus m square here, m minus m is 0, m minus m is 0, m square plus 1. So, therefore, this is the inverse. Is that okay? Now, if I multiply these two, I get 1 minus m square, m plus m is 2m. So, I wrote it wrongly, I think, m here and plus m 2m itself. So, please I will have to go back, m square and minus 1, m square minus 1. all right. So it means that I wrote it wrongly there, so let me go back here and see what was the mistake. So it says that it should be this here itself, minus 4m squared should be here. So it should be minus 4m squared itself. I use the green pen. So it should be minus itself here. So all right, it should be minus 4m squared. So minus, oh, so it is correct, yeah. So this part is correct. So that was the mistake. I took it wrongly. Fine. So correct yourself. This is how you learn that you do mistakes, then you come back and do the corrections by different ideas. So here I had calculated using without calculating this, the image of 0, 1. I tried myself, there was a mistake in this calculation at this stage, and therefore that mistake cropped up. But once I look at from the other direction, I am able to get that what should it be. Fine. So again, if I want to go in R3, fine. If I want to reflect anything in R3, what will happen is that I have a line here. Now there will be plane. Fine. So if I look at this line, I want to have a point here which should get reflected here. Fine. If I want to get reflected here, this line is there. So this reflection will give me this part. And what happens? If I take anything like this here, fine, there is no change there itself because it will remain as it is. So what will happen is that I will get this, whatever this t is for me, and I will get 0 here, 0 here, 1 here, all right. So again I will get something like this. So I would like you to understand these small ideas which are very important for us, fine. The next thing we would like you to understand is the last thing that we had done in the previous class, and that was to do with, so suppose I have a matrix T, so I have a map T of x was S of x, this is what the was, and we had basis of Rn. So T was a map from Rn to Rn, and I had a basis A here. So we wanted to write A, we had A as well as the basis B, wanted to see, so A is for the domain, B for codomain, I think, and we wanted to write T of x in the basis of this. So this was equal to, what you have to do was, you have A as the matrix here, basis matrix, you have a B as the basis matrix. So what we had learned was that since it is in Rn, so any V with respect to this B will be equal to B inverse V itself, all right. So we would like to use that idea. So here it will be B inverse T of x, fine. So T of x we want it in terms of this, so that I have already taken care of B. Now I want to write this part in terms of A. So want T of x, so not like this, I should write it correctly, otherwise there will be a problem for you. So this is equal to B inverse of T of, I don't know how should I write, V1, B inverse T of V2, B inverse T of Vn, where this has basis V1, V2, Vn. Then you took out V here, from everywhere V inverse, B inverse, B inverse is outside, and T of V1 is S of V1, S of V2, S of V1. So this was same as B inverse of S of V1, V2, Vn, but these are in a standard basis. So we wanted to write it in terms of A, all right, and therefore the idea of A inverse will come into play, fine, and therefore what we saw was that this matrix T of AB, this matrix turns out to be B inverse SA, fine. So you can see here, again each have to be written in terms of A, so A will come, and this is what we had, this was your T of AB. So recall this part, you recall, fine. Now, so questions that I had asked, T of AA by definition is, if I go from here, it will be A inverse SA, T of BB will be equal to B inverse SA. How are they related? So they are related with the idea that I can write S as, look at this part, S is A times T of A of A inverse. This is also equal to, from here, sorry, here it is B, because it is BB here. So S is equal to B times T of BB of B inverse. So using these two, what we see here is that T of AA will be equal to, this will be equal to multiply. So I have already B here, T of BB B inverse. So I am writing this, so A inverse is here, so it will go as A, and A is on the left, so it will go as A inverse. So this is same as, look at this, this is just the inverse of this part. So B inverse A whole inverse T of BB and then B inverse A. Fine. So this is the way we wrote, and recall that B inverse A was the matrix of identity. So I had written, I think I had written that, so recall there was this map identity of, I wrote it as BA as A inverse B. Here looking at B inverse A, and therefore this is identity of from A to B. All right. So again, be careful. This was the notation that I had used, notation. All right. So let's match it here. S is here the identity map, and therefore you get B inverse A going from A to B, A to B. S is the identity map for me. So S is replaced by the identity. So here it is B inverse identity, which is I sub n of A, which is same as B inverse A. Fine. So what was identity map? Recall, identity of this vector space V was V for all V belonging to capital V. All right. So this is what we had. So here it is Rn itself for us. So it is, so ID of EI is EI 1 less than equal to I less than equal to N. Fine. So it is the same map, that it does not do anything. The only thing we are doing here is that we are going from basis vector A to the basis vector B. We get this. Fine. So what I would like you to check here is that going from AA to BB requires us to multiply this. All right. So we would like to understand this nicely using what are called similarity transformation. It's going to be a bit confusing. So be careful, understand it, that how do I go from one to the other. All right. And then we will build upon it. So that's all for now. Thank you.